So this lesson will be about how we make oxidation and reduction useful. We're going to look at some devices that can allow us to harness the electron flow in a redox process. So I'm going to demo this in class for you, this redox process. And in it, we're going to put a piece of copper wire into a solution of silver nitrate, and you will see a single replacement reaction happening in which the Ag plus ions are reduced to Ag solid metal, and the copper metal is oxidized to copper 2 plus ions. Okay, this is similar to the oxidation reduction that happened with metals in your lab. In fact, I think you did this reaction in one of your wells. Here's the net ionic equation, all right? And it should be pretty easy to identify the loss and gain of electrons. Copper lost 2 electrons, silver gained 1 electron. And in order to balance it, I would need to do this so that the number of electrons is 2 lost, 2 gained. They must be equal. So I'm going to take a few minutes here to diagram what's happening as much as possible on a particle level for you. So let me get started. We start with the silver nitrate solution, and the copper wire is immersed in that solution. You will see that silver metal, it's going to look kind of grayish at first, begins to build up on the surface of the copper wire where it is below the surface of the solution. The part you can't see is that the copper wire is turning into copper 2 plus ions, although eventually you will see the solution take on a bit of a light blue tinge, should start to become slightly bluish, and the processes that are happening are the reduction of the silver ions and the oxidation of the copper metal. Evidence is the bluish color of the solution, okay, and the appearance of the solid metal. So what we really have is electrons being transmitted between two substances, okay? And electron movement is electricity. So the question is, can we make this process useful? And the answer, as you'll see, is yes. So I will next diagram how we could set up a very fundamental voltaic cell with the same ingredients that you had in the beaker or test tube with the copper wire and the silver solution. So the first thing I'm going to do is I'm going to separate the two reactants. If you remember, the reaction that was happening is that copper solid was losing electrons to silver plus ions, making copper ions and silver metal. And if I allow these two reactants to touch each other, they're going to do it on contact. I need to separate them. The other thing I'm doing is I'm putting the copper in a different form. I'm making it into sort of a rectangular flat paddle of copper, which is going to give me more surface area. I'm going to connect that copper using a piece of wire to another electrode. We'll talk about what that electrode will be made of down the line a little bit, but let's let it just be sort of an inert metal that won't react, that is there to make contact with the silver solution for the moment. The last piece of this is there is no circuit here. I don't have a circuit until I connect and I have a loop. All right? This is a sort of a straight line between one beaker and another. My connection is something called a salt bridge, which is an U-shaped tube filled with some ionic solution. We like to pick ions to put in our salt bridge, dissolved in water, that are not going to precipitate or bother anybody, okay? So I'm going to put in my salt bridge some positive and some negative ions. All right, and what I do is I dissolve that in water. I have the U-shaped tube like this. I pour the solution in so that it fills this whole solution, whole U-tube, and then I put a little piece of cotton at the two entrances, all right, just to kind of keep it from spilling, and I flip it over and connect it drop one end in each of these two beakers. So that's how I install a salt bridge. Once the circuit is completed by the addition of the salt bridge, there will be a natural tendency of electrons to flow in the direction of the silver ions, which are in contact with this metal. You remember metals are good conductors, and the attraction for electrons of a silver plus is greater than that of a copper. So there will be electrons here in this metal, because metals contain electrons, right? That the silver ion will grab and turn into silver at the surface. And since there's probably, let's say, 1 molar silver in the solution, there's plenty of silver to be able to grab those electrons and turn into silver metal on the surface of that electrode. As those electrons are consumed, electrons will be drawn from the piece of metal here, causing copper 2 plus aqueous to go into solution. Okay, and so the copper will oxidize to form copper 2 plus, and 2 electrons will be sent along the wire. Now I guess I should be consistent. These would have to balance. So for every 1 copper atom that is oxidized, 2 silver atoms will be formed. So there is a ratio going on here in this process. Okay? And so I complete the circuit, and there's a natural flow of electrons from the copper electrode to the silver solution. This electrode where this oxidation process is happening is called the anode. The other electrode is called the cathode. One last piece here. Since I am producing positive ions in my compartment here, the solution in the left-hand cell, half cell, would get increasingly positive. And so what happens is negative ions from the salt bridge flow in to cancel or balance the charge of the positive copper ions that are being made. I am losing positive ions in this other compartment, but I still have negatives remaining, and so positives flow in this direction to balance the charge. So the role of the salt bridge is to have positive and negative ions present that can flow to either compartment to avoid the buildup of a charge in those two compartments. On this screen, you see the picture from your textbook, figure 20.5, depicting exactly the same thing with a slightly different process. In this case, zinc is the oxidizing metal, and copper ions are being reduced, but still the cathode is where the reduction takes place. The anode is where the oxidation takes place. You can see a direction of electron flow, which is always from the anode to the cathode, and you can see a direction of ion flow that must counteract the direction of electron flow. Okay, so there's this whole big process happening with things flowing from left to right through the wire and right to left through the solution so that no net charge builds up anywhere, and a nice picture of the particle level view of this. This is a table from your book that is very much worth looking at because it puts reduction reactions. For now, you can ignore the E0 value, okay? Call that a numerical score for how favorable the process is. What we have at the top here are the most favorable reductions. And as you read farther down, and there's a lot more of this table that didn't get put into this slide, we get less favorable reductions. Okay, but they are all reduction processes. And this will help us choose, where will a reduction happen and where will an oxidation happen? And you'll see how that plays in the next couple of slides. Just pause for a moment and read this slide over, if you would like. We'll get into more details about this later, okay, but I guess the big takeaway, if you compare the voltages of two processes, the more positive value is more favorable. And that's kind of where you can leave it for this particular lesson. Last thing to talk about in this lesson is calculating the voltage of a battery. It's very easy to do. You locate your reduction and oxidation processes. Go back and balance this equation. And use the voltage tables. Okay, so if you look at the tables in the appendix of your book, the reduction of silver is at a voltage of 0.80 volts, and the oxidation of copper, now keep in mind, when you're looking at the reduction table, you're seeing the reduction of copper. Now we're looking at the oxidation of copper, so you have to change the sign. We will talk about this in class. And the oxidation of copper is negative 0.34 volts. So when you sum these up, E0 of this cell is 0.46 volts, which is positive, which is favorable and spontaneous. We will talk about this when we get together. Thanks for watching.